Good morning and welcome to my talk. I'm Uliana Alexieva and I'm going to tell you about the parallelization in FLEUR and how it's possible to simulate large unit cells with our code. But first, why actually bother? The reason is that the execution time scales cubically with system size and memory usage scale quadratically. I have some estimations here in the table. If you calculate a system with 64 atoms on a single core, your calculation will be complete in 1 hour, and you will use about 3 GB of memory. Everyone's happy. But if you want to go further, if you want to calculate a larger system, are you willing to wait 2 days or more? And even if you are, will such a system fit into your memory? Into the memory of your computer? For example, a laptop has memory about 16 gigabytes. But maybe you have a bigger machine. Maybe you have a workstation with tens of cores, or maybe you have an access to a supercomputer. Now the question is it possible to run FLEUR on such machines? And the answer is yes. And this is what my talk is about. I'm going to tell you about parallel programming in general a little bit. Then I will explain the parallelization of FLEUR, and then I will give you a couple of examples what is possible with FLEUR now and what we are aiming for. On the picture you can see a node of a cluster, but for us it's a simplified view is enough. A cluster consists of many nodes connected by a network, and inside the node we have several compute cores which have access to a local memory. And already from this picture we can see that we have we need two programming paradigms. We need a possibility to access the local memory, to be able to work with several cores on the memory at the same time, but we also need to be able to access memory of another node, to be able to send messages by a network. And this brings us to two parallel programming paradigms, shared memory and distributed memory. We start with the shared memory parallel programming. Here, memory is accessible for all processors. Everyone can write and read data, and you have no need for explicit communication. What we need for what we use for that in FLEUR, we use OpenMP. You can see an example of the code on the slide. You put the pragma, and the execution of your code is sequential. Before it runs only one core, but as soon as the execution achieves this place, the team of workers, the team of threads will start and work on the code concurrently. In the distributed memory parallel programming, each processor only can access its own memory. So you need to send messages, you need to communicate explicitly, you need to provide information who is sending what to whom. We use MPI for that in FLEUR, message passing interface. Again, you can see an example of the code here. This is a receive call, and this is the send call. How does the execution model look like? Let's start with pure MPI. When you have MPI parallelization in your code, you start several processes from the beginning, and then run your code, and from time to time they communicate by sending in messages. If you have only OpenMP, then your execution starts with one process. This is also called master thread, and it executes your code serially. But at some point it comes to a parallel region, and then it starts its team of workers, and then they work together on the parallel region of your code. If you have them together, MPI and OpenMP, then you start your program with MPI processes, and then each of them becomes a master thread, which has its own team of workers, of OpenMP thread workers. If I want to run a code on such a machine, I have a choice, right? For example, here I have 24 cores. What is the best strategy to map? I can start one MPI processes and span it over the node. I can have two. I can have it. Can make it master of 24 threads, or maybe it's better to start two MPI processes. Usually, yeah, you will have to test, but sometimes you want to. It's better to know the real architecture of your node. For example, here I know that my node consists of two separate sockets, and it's better to have at least one MPI process per socket. What you definitely don't want to do here is start 3 MPI processes per node, because in this case, these threads of one process will be thread between two sockets. This is not good for the performance. Now let's move to FLEUR. As you know, FLEUR is a DFT program. So basically what you're doing, you are solving a generalized eigenvalue problem. Then you use the solution to construct the charge density, but actually you also need charge density to construct such a problem. So you have your problem is self-consistent and you solve it iteratively. You make an initial guess, and then you use this initial charge density to calculate potential. Then you set up the matrices for eigenvalue problem, and then you solve the eigenvalue problem by diagonalization. Then you calculate new charge density. If it differs too much from the initial, you repeat the whole cycle again. These 4 parts of the code, they are very different algorithmically. They scale differently, but they also, the time consumption differs a bit from system to system. But usually the matrix setup and diagonalization are the most heavy computationally. They can take up to the half of the execution time. The scaling is also different. The potential scales quadratically with the system size, and the remaining 3 scale cubically. As you can see here, I put several boxes here. This reflects the fact that sometimes you need to sample your Boolean down with a set of k points and then solve this eigenvalue problem for every k point. And from the point of view of parallelization, this is actually awesome, because you have several completely independent, computationally heavy parts which you can distribute, and they won't communicate. So you can expect the parallelization be very effective. And this is indeed what we do. Our top level of parallelization is MPI parallelization over k points. Then we can also spread our eigenvalue problem over several MPI processes. And then, of course, we have multi-threading with MPI. Let's check how it works. On the plot, you see speed up. What's that? We start the same, we run the same calculation on 1 node, on 2 nodes, on 4 nodes. And ideally, we would expect that our calculation becomes 2 times faster, 4 times faster, and so on. This ideal behavior is plotted here. This is this gray line. And we can see that the real speed up, this total speed up is red, is indeed very, very close to the ideal. So this parallelization over key points is indeed very, very effective. So if you have a system with several k points, make sure that you use this parallelization. And try to adjust number of k points to the number of MPI processes. What do I mean? FLEUR will try to distribute your calculation in such a way that the load balance is maximized. That means if you have, for example, 4 k points and you start your calculation on 3 MPI processes, then it will distribute every K point over 3 MPI processes so that the K points are calculated subsequently, one after another. But if you start 4 K points with four MPI processes, then each MPI process will get its own K point. So try to adjust the number of K points, or the number of MPI processes. The next level of parallelization is eigenvector parallelization. Again, you can see the speed up plot here. You can see that it gives you an additional speed up, but there is also a second advantage. It will allow you to tackle larger systems, because at some point your unit cell will be so large that it won't fit on one node into the memory anymore. You can see how the memory usage drops when increasing number of MPI processes here. And you can see this behavior that at some point it achieves a plateau. So for these particular systems, doesn't matter how many MPI processes you need, the memory usage will not go under 2 gigabytes. And this behavior is general. For every system, there is some plateau, there is some minimal memory per MPI, memory consumption, memory usage. And this amount will grow with the system size. So again, at some point you achieve the situation when you won't be able to fill your node only with MPI processes. So this is another reason why you need a multi-threading here. And that is this example. Let's start with non-magnetic Unix cells. Here on the plot, you again see the scaling, but now it's not a speed up, but it shows you how execution times drops with when you increase number of nodes. And there are 3 systems here, all with over 1,000 of atoms. And the biggest one is strontium titanate. You can see the unit cell here. It's an extended defect. Let's take a closer look what we have here. So this system have almost 4,000 atoms. The calculation were done with 4 K points. And for that, we needed 1,000 of nodes. The matrices for eigenvalue problem, you have 2 of them, remember? And they're dense and Hermitian. Actually, it wasn't complex in this case, but it was dense. The size of the matrix, the length of the matrix is 345,000 elements. And this is the reason why the scaling starts here at 256 nodes. Because it's not possible to squeeze the system into less amount of nodes, into smaller amounts of nodes. Why is it interesting to calculate such a system? It helps to understand the physics of an extended defect. It's important for membristic phenomena. But as you already know, the real area of expertise of FLEUR is magnetism. And here, the ability to calculate larger systems opens truly new perspectives. One of the recent topics is complex spin structures on the atomic scale. And such systems, topological protection leads to stabilization, to the formation of the so-called quasi-particles. And these are possible candidates for large amount of application, for example, data processing and neuromorphic computing. And so far, the procedure to study such system was a multi-scale approach. You first do DFT calculation to extract some parameters, to extract some material properties, and then you use these parameters to run spin dynamic simulations. But now it slowly becomes possible not only to verify this multi-scale model, but also to understand how exactly the electronic structure is affected by the complex magnetism and these in such structures. And this is an example. You can see the unit cell here on the right side. And you see the magnetization vectors outside the structure. This is called globule. This is a globule in manganese germanium. And in the system, we have about 1,000 of atoms. And you see that outside the globule, all the magnetization vectors shows in one direction, up. Inside the globule, we have vortices, so that in the middle, on the axis, the magnetization shows down. So here at the edges, you have a point where adjacent magnetization vectors look in different directions. These are called Bloch points. And the existence of such points shows you that the continuum model cannot explain the physics here. It's a singularity, so it does not provide you information what exactly happens here. So that is the reason why it's very interesting to be able to simulate such simulation with a DFT code. To converge such a system, remember it's magnetic, so the matrix is 2 times larger. You will need 2 million core hours on a machine which called SuperMUC G in Munich. Our optimization and parallelization activity are part of our work inside the MAX project. MAX is European Center of Excellence, and MAX stands for Material Design and the Exascale. At the moment, the top 1 computer in the world is called Fugaku, and it has over 400 petaflops. So it's pretty close to the exascale, and we are preparing our code for the exascale machines. And when they come, it will be very exciting because it opens, again, further possibilities. I was talking about single magnetic structure which already can use up to 1 million of core hours, but with exascale machine, it will be possible to relax the system, to understand how it evolves in time. And besides that, sometimes it's interesting not to simulate one system, but simulate the whole family of the systems, to do kind of virtual screening of these materials. You see the logo of AIDA here. This is what you will learn in the next lectures. So this is very exciting. Now I come to the summary of my talk. So I told you the modern HPC clusters are very complicated systems, and you need parallel programming to deal with them. And FLEUR is part of the MAX project, and it has 3 levels of parallelization: MPI over K points, MPI over eigenvectors, and multithreading. It can be used on HPC clusters, and it is able to simulate large unit cells with thousands of atoms. Thank you very much.